All right, good afternoon, everybody. Let's get started. So, today we're going to continue our journey into both building increasingly complex and sophisticated and interesting combinational circuits, and also learning a few more language features from Minispec so that we can do that efficiently. So today's lecture has these two goals. We're going to if you remember from last lecture, we ended up in a place where we said, well, we have functions, and we can essentially invoke those functions, which inlines them in our circuit, which gives us this great tool that then we can reuse small functions to build larger ones. But that got kind of tedious. So today we're going to, in the first half of the lecture, discuss some features that will make it easier for you to write large circuits very succinctly and very efficiently. And then in the second part of the lecture, we're going to shift gears and talk about design trade-offs, about area, delay, power trade-offs in different circuits, and how the algorithm that you choose ultimately has a big impact in the implementation, in the area and timing characteristics of your whole design. And we'll do that by studying different auto implementations, and that's a good case study because you'll actually get to use that in Lab 4. But before we dive into today's material, let's spend a couple of minutes talking about or finishing our discussion on shifts. So remember, last lecture we started with the ripple carry adder, then we saw multiplexers, and then we ended up looking at shifts. And remember that if you want to do a fixed size shift in hardware, right? You have this 4-bit value here, and you want to shift right by 2 bits. That's really easy, right? That's just wires. So this does shift right by 2, and we can write this in a more succinct form, right? We can just express this as this block. So you have, remember, this notation where this 4 denotes that this is a 4-bit input x, and then this returns a 4-bit output x. That's x shifted right by 2, right? But then we tried to do these variable size shifts, right? So in RISC-V and in most other processors, you have the shift instructions that actually let you specify how much you want to shift the value by. And in particular, if you want to do logical right shift, then suppose that we have 32-bit values, just like in RISC-V. We have some parameter n or some argument n that is between 0 and 31, and it's specifying the amount of shifting that we would like to do, right? So one simple implementation that we saw was, well, we know about multiplexers and we know about shifters, so let's just combine them, right? We can have 32 different fixed size shifts, right, from 0 to 31. So those are all the ranges of shift rights that you can do, and then we can just choose which one we want with a 32-way multiplexer, right? Using this 5-bit n input that tells us how much to shift. So remember that we said, well, this is, obvious, but it is inefficient, right? Because this, although it looks very nice, just like a single multiplexer, that internally has a lot of logic, right? This is 1,000 wires, right? It's 32 times 32 input wires to this mux. And remember, each 32-way mux was done with a tree of 31 2-way muxes, right? And in general, an n-way mux is done with a tree of n minus 1, right? 2-way muxes. And then we have n of those. In this case, n equals 32. So we have n times n minus 1 2-way 1-bit muxes. And that's just a lot of logic. That's 1,000 muxes, 1,000 1-bit muxes, about 3,000 gates. I think we can do better. So to do better, it's actually not that hard. To do this efficiently, this is what we call a barrel shifter. And the only thing we need to do is to realize that we can do a shift by n as a sequence of shifts by power of 2 values. So for example, suppose that you want to shift right by 5. Well, what's the binary encoding of 5? It's 101, right? So 5 is 4 plus 1. And you can do shift by 5 by doing a shift by 4 and then a shift by 1. Right? So if you do a sequence of shifts by power of 2 sizes, you can get any shift you want. Not only that, but the bit encoding, right, the binary representation of n tells us which of the shifts are needed, right? So in particular, if the ith bit of n is 1, then we want to shift by 2 to the power of I, right? So again, going back to shift by 5, 5 is 1, 0, 1. If you express it as a 5-bit value, right, it's 0, 0, 1, 0, 1. So we want to shift by 2 to the power of 2, 4, right? That's the uppermost 0. And then to the power of 0, 1, that's the lower 0. Okay, so how do we translate this insight into hardware? Well, just do a sequence or a cascade of multiplexers. And then in each of these steps, right, basically we're selecting whether we want to not shift or shift by a power of 2. And the value that we're going to use to select whether we want to shift or not is the ith bit, right? So the ith bit of the n variable, the n argument. So if n4 is 1, then we want to shift by 2 to the 4, shift by 16. Likewise, if n3 is 1, then we want to shift by 8. If n2 is 1, then we want to shift by 4, and so on. Can you see how this sequence of 5 multiplexers with essentially wires, right, the same input wired differently, is giving you the same, the behavior that we want? Okay, now why is this better? Can any of you tell me how many two-way 1-bit maxes does this require? Let's build it out. So how many 2-bit one-way maxes do we require for a single one of these maxes? This is a 32-bit max, 32-bit two-way max. And remember, a multiplexer that takes 32-bit inputs, it's just 32 1-bit multiplexers in parallel. Right? So each of these is 32 1-bit two-way maxes. So that each of these is 32, right? How many do we have? Anybody? How many maxes are there here? 5. And in general, if we were doing n-bit values, right, we would need log n or log base 2 of n, because our selection variable would have log 2n bits, right? So in general, this is n log n. So instead of growing quadratically, instead of growing with n times n minus 1, this now grows with n log n, much better, right? Remember, we said the previous one was 1,000 maxes. This is about 100, right? 150, 160. So we're reducing the size of the shift circuit by almost a factor of 10, right? Just by using a better algorithm. Okay, any questions? All right, so remember where we ended up last time was with code like this one, right? So we started looking at the basic features of minispec, and we used a ripple carry-adder as an example to, drive the different features that we saw. So remember that we said, well, the key thing you want to do is write small functions and then compose them, right? So we said, well, if you want to build a ripple carry-adder, you can start by designing a full adder, right? A circuit that adds 3 1-bit numbers and gives you a 2-bit number, and then combine them to build, in this case, a 2-bit ripple carry-adder, right? And then you can combine 2 of those, as shown here, right, where we have a 4-bit ripple carry-adder that is composed of 2 2-bit ripple carry adders, each of which computes the upper half and the lower half of the output. So we could keep going, right, and say, okay, we want to do a 32-bit ripple carry adder. So we're going to define RCA8, which uses 2 RCA4s, RCA16, which uses 2 RCA8s, and RCA32, which uses 2 RCA16s. Right? You could do that today with what you know so far. However, this is extremely tedious, and not only is it tedious, it's actually repetitive. Right? You're doing the same thing all over and over again, just changing the indices here. But it's the same template. It's the same generic algorithm, combining two things and building a larger one. So what I want to do today is basically focus on one feature of Minispec that's going to let you automate this. It's going to let you use the compiler to do the dirty work. And that feature is called parametrics, which sounds like a very scary word, but it's actually a very simple concept. In fact, let me start with one instance of parametrics that we've already seen, which is called parametric types. And we've already seen one parametric type. This is bit n. Right? So we said bit n is a type that represents an n-bit value. And this is one parametric type. What does it mean to be a parametric type? Well, it just means that it's a generic type. Right? It's not, you cannot just go and use bit n in your circuit. Right? In this case, n is what we call the parameter of this type. It's an integer, it's a number. Right? And if you want to use it in your circuit, you have to give it a particular number. Right? You can't just say bit n blah equals something else. You have to say, well, bit 4 or bit 5 or bit 16. Right? And then make it into a concrete type with some fixed number of bits. Right? Because remember, in the end, we are building combinational circuits. So functions have to have a fixed number of bits coming in, going out. Right? Any questions? Okay, so not only you get bit n, but Minispec also has several other parametric types, and in fact it lets you define your own. So we'll see them later. I don't want to focus too much on parametric types, just basically remember that they're generic types that then, once you give them a particular value for the parameters, they become concrete. And those parameters need to be known at compile time. You cannot have this be a variable, right, this n be a variable that's unknown until you actually evaluate or run the program. It's not a program, right? You can't just run this. This is producing hardware, right? So this n needs to be known to be a particular value by the compiler to generate a circuit, right? And just a detail that parameters can be integers or types. So we've only seen bit n, but for example, you have vector of nt is an n-element vector of t's. We'll use this when we build a processor. A register file is a vector of 32-bit registers. But for example, if you say vector for bit 8 is a 4-element vector of 8-bit values. Okay, so you see this weird syntax with the hash, right, and open parentheses, parameters, close parentheses, right? Now this concept of parametrics is actually a very powerful concept because essentially it lets you define generic things that work for a whole range of cases. And types are one aspect of this, but the other important aspect is parametric functions. And this, by the way, is the one feature I'm going to focus on the most. The rest of the features of Minispec, we'll see them fairly quickly. But I want to focus on this one first because it's likely you haven't seen it. It's also very general, right? So most statically typed languages have some notion of generics or templates. C++ has templates, Java has generics, and so on. Right? So you're going to see this all over the place. But it's actually more important in combinational logic. So this concept is far more fundamental in hardware when you're building hardware than when you're building software. Because in hardware you can do fewer things. In hardware you cannot take some variable number of bits as the input with combinational logic, right? You just have a fixed number of bits. And this is why this is much more important, a much more important concept. Okay, So going back to functions, right? We've talked about parametric types. What about functions, right? Ultimately, as I said before, we have to have fixed arguments and types, and this creates two problems. The first problem is that, if I want to do some family of others, let's say, I need to write a function for every bit width, right? I need to write RCA 32, 64, 47, and what have you, and that's just a lot of boilerplate. The second one is, and we've seen this with the example, right? If we build large functions from smaller ones, which we say was a really good strategy, now we have to write many functions. And this just gets very, very, very tedious, right? So RCA2, RCA4, RCA8, keep going. Okay, so parametric functions essentially let us solve both problems at once. A parametric function is just a generic function that works for all cases that you care about. So in this case, for example, you could write RCA of n, an n-bit ripple carry-adder, where n is a parameter. And so whenever code uses this function, it will then call it with a particular value of n, and that will instantiate a particular circuit. So for example, RCA, some other function might call RCA 32, and that will create a 32-bit adder. Okay, let's see a concrete example of this with a function that's simpler than the ripple carry adder, and then we'll see how to extend this to a ripple carry adder. So we've talked about parity, and we saw how to do the parity of 2 bits, 3 bits, and you can generalize this to n bits, right? What is the parity of an n-bit number? Is the XOR of all the individual bits. And how do you express this with a parametric function? Well, with this function over here. This one-liner over here is packing a lot of meaning, so let's go over it. This is basically saying you have a parity function that takes a parameter that's an integer n. Okay, that's the number of bits of the input. Now that n shows up as a variable everywhere else in the function, including as an argument. Right? This parametric function is taking a bit n, an n-bit input. And then this function says, well, if n is 1, then just return x, right? Because x is a 1-bit value, and that's just the parity of x if x is x, if x is 1 bit. And if it's larger than 1, then take the most significant bit, x of n minus 1, and XOR it with the output of parity of n minus 1, which then takes x of n minus 2 of 0. So take all the other remaining bits, all the bits except the most significant one, run those through parity of n minus 1, take the output and XOR it with x of n minus 1. Okay, so there's a lot of stuff going on here, right? First of all, note that the parameter is used as a variable throughout the function. So now we have things like bit n, which I said you can't have, right? You can't. This is not a circuit. This is not a valid circuit. It takes some variable number of bits as an input. What is that? You can't just have n wires going into a circuit. So this is now a variable. And then note that we're achieving this thing that we wanted to do, having larger circuits by composing them from smaller ones, right? By having parity of n invoking parity of n minus 1. But so then the magic is, how does the compiler interpret this? Because there's one extra step that happens. Right? And so let's say that some other function calls parity of 3. So the compiler will look at that and say, okay, let me produce a code for parity of 3. So wherever you have n, it plugs in a 3. And whenever you have an expression that depends on n, it just evaluates that expression. Right? So it will say, okay, so parity of 3, it takes a bit 3x, which returns x of 2 XOR parity of 2 of x1, 0. Okay, now that's a function. That's a real function. That's a concrete instance of a function. Right? This you can build hardware for. But then the compiler will take a look and say, oh, okay, that function actually wants parity of 2. Let me generate that. So, okay, n is 2, so larger than 1, so it will go to this branch and generate just that. and it will say, well, looks like this function uses parity of 1. Let me go and generate parity of 1. Okay, that just returns x, right? What hardware does this correspond to? With what we know so far, can you take this code, which, by the way, this is valid, you could write it that way. You could write this particular code just like that and it works. What hardware does this map to? Well, so parity of 3 is an XOR gate, right? That takes x2 and then instantiates parity of 2. What is parity 2? Well, it's another XOR gate. It calls parity 1. So in lines parity of 1. And what is parity 1? It's a wire, right? Okay. Any questions? All right, so given this, now notice that we're writing a generic description, and then we're letting the compiler do all this unfolding of this generic function. Right, so the compiler is actually just doing the dirty work for us. What we did in the previous lecture manually, we're now doing automatically. But that's all. Right? There's no magic here. All we're doing is writing code in a particular way so that the compiler can do the dirty work for us. Okay, there's one small detail here, which is that how do we know, or how does the compiler guarantee that it's going to evaluate what we expect at compile time? And this is done through this integer type. So integer is a special type that is always, it's guaranteed to be evaluated by the compiler. To ensure this, we actually make integer values just numbers. They can be positive or negative, and they can have an unbounded number of bits. And since things with an unbounded number of bits cannot be synthesized into hardware, right, you better be damn sure that no integer is ever going to make it to a circuit, right? So what happens is the compiler is going to go and take all integer variables and turn them into fixed numbers. And whatever it cannot evaluate, it's just going to print an error. It's just going to say, you know, this value is not something I can figure out. Please do something else. And then integers support all the same operations as bit and as n-bit values. So we have arithmetic operations, logical comparisons, logarithms, and so on. But they're evaluated by the compiler. So when you type things like n minus 1, here, note how there's no subtractor circuit, right? The compiler is taking this n minus 1 and then elaborating it or substituting it into a particular value. All those operations happen at compile time. And this is a very important thing to keep in mind. Okay, so with that, let's take a look at the n-bit ripple carry-adder. Right? This is where we wanted to get to. We want to have a generic circuit, RCA of n, and one way to build it, we could build it like before by combining two RCAs of n over 2, but instead we can just combine a full adder and an RCA of n minus 1, just like we did with the parity function. Right? So this is how it looks like. Right? How do we fill this in? Well, remember the code that I showed you before. We did lower, upper. In this case, we're going to call this lower, right? So the n minus 1 is going to be the lower part. So we just call RCA of n minus 1 with all the bits of A and B except the most significant ones. And then this is going to return an n-bit result. We're going to use the upper bit as input to this full adder, right? And then this is going to generate a 2-bit value, upper 0, upper 1. And we just need to return that 2-bit value as the two most significant bits, and then the remaining bits of the output of RCA of n minus 1. Okay, am I done here or am I missing something? There's something missing, right? So the compiler is going to look at this and say, okay, RCA 47, we'll start doing RCA 46, 45, 44, blah, 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 till it gets to RCA of 1. And then what will it do? RCA of 0, RCA of -1, RCA of -2, -3. And at that point, you have a bit of negative values, which probably doesn't work. So you can define just a base case, right? And that will make the recursion stop. Essentially, you say RCA of 1, just use that one. Don't make up your own. Okay? So this is just the same concept as using recursion, right? This is our induction step. This is our base case. But we're doing it at compile time. And this is very important because remember, functions are in line, so you cannot have recursive functions. But you can have recursion on the parameters. Okay. Any questions? Cool. So, with this, you can do pretty much anything. There's a few features that I want to spend 5 minutes on that are described in far more detail in the tutorial. And the main reason I want to spend some time on them is, especially with the last two ones that we're going to see, is that they're tricky. Okay, so the first one, we're going to spend a couple of slides talking about types because types are useful. The first thing is minispec has type inference. So we've been writing the type of each variable explicitly. But if the compiler can deduce the type of this expression on the right-hand side, then you can just type let, and the compiler will deduce the type of the variable that you're declaring. So for example, here, we declare x to be a bit 4 variable, and then we say, if you say y equals x, let y equals x, then the compiler deduces, well, y must have type bit 4. Right? So this is just saving you type. Same, you can do this with more complex expressions. So if you concatenate x with x, then C will have type bit 8, and so on. Okay. Minispec also allows you to define your own user-defined types. And this is very helpful when you have more complex circuits. And this is, by the way, exactly the same syntax as C. So on the one hand, you have type synonyms, which let you give a different name to an existing type. So for example, if you're building a circuit that manipulates bytes, 8-bit values, it's nicer to just use bytes rather than bit 8, bit 8, bit 8 all over the place. Right? It's shorter, it conveys things more clearly. So you can take any existing type and redefine it to be, or give it a new name. That's a type synonym. This is with this syntax. Type def, name of the existing type, name of the new type. Okay, then you have structs, which just represent what we call a composite type. This is a group of different member values with their different types. So for example, let's say that you're building an image processing system, right? You're building some image processing hardware, and it manipulates pixels. And pixels are commonly represented with as 24-bit values that have 3 components. They're red component, green component, and blue components, each of which is represented as an 8-bit value. So you could just put bit 24s all over the place and then just do bit slicing to get the red, green, and blue components. Or you can say, look, I have a type byte that is a type pixel, right? So this is the name of the new type that you're defining. And it's composed of 3 different members, red, green, and blue, all of which have type byte. And then you can instantiate, you can create a variable pixel and access its members directly. You can say p.red equals whatever. Finally, we have enums or enumerations, which just let you define a type that consists of a set of possible values that are represented as symbolic constants, as symbols. So for example, let's say that you're building some circuit that's going through different states, right? So it starts in some ready state. Whenever it gets an input, it goes to a busy state. If something goes wrong, it goes to an error state. So you can just encode this with this enum here. Type def enum, then you say all the different labels that you want to have, and finish with the name of the type. And then you can declare variables and assign them particular values. Now, the key benefit of structs and enums is that they're much more clear, right? They convey intent much more clearly than just manipulating bits. Ultimately, all of these things are translated to bits, right? So every pixel is going to be a 24-bit value in hardware. Every state, how many bits is state going to be? This state variable over here. How many states do I have here? 3, right? How many bits do I need to represent 3 things? 2. So this is going to be a 2-bit value. But imagine how messy it would be to say bit 2 state equals 0, 0. If state equals 0, 0, then move state to 0, 1. That just is very unclear. And so the benefit here is that it's much clearer to use this than to use raw bits. Yes?
Can the number values in structs have different sizes?
Yes. Yeah. So this just shows 3 bytes, but you could have, bytes and bit 16s and vectors and what have you. And in fact, you can have structs composed of other structs. And in fact, structs and type synonyms can also be parametric. So for example, you can create a pair of T, and that's 2 T's. Yes?
What would be the internal representation of the nums? Like, for example, will this state be represented to be integer?
So this is all described in the reference. Basically, the compiler will assign values sequentially unless you tell it otherwise. So ready will have representation 0, 0, then 0, 1, then 1, 0. But you can change that, and that's all in the manual. Okay, 2 features. There are 2 advanced features that I want to spend a couple of minutes discussing, because they're false friends. They're things that look like software constructs, but they're actually quite different. The first one is for loops. So for loops allow to let you express a sequence of similar statements in a very compact way. For example, you have this for loop over here, which has a syntax, again, very similar to the syntax of C. What this loop says is you have an induction variable that's an integer I that starts being 0, and while I is less than 6, you have to evaluate this or unfold an iteration of this and then increment or change the induction variable as given by this update statement here, right? So this will essentially first unroll I equals 0, then I equals 1, 2, 3, 4, 5, and then you will get to 6, and that's the end of the loop. Looks very similar to for loops in software. It's nothing like for loops in software. The number of iterations is fixed at compile time. You can see this because your induction variable is an integer and must be an integer, and if you put anything other than an integer there, the compiler will say, "What are you doing? Shut up. Give me an integer. I don't know how to do anything that's not an integer." And the reason is that these loops are unrolled at compile time. So this is just a compact way of writing this sequence of 6 statements over here. Okay? You are not jumping back to a previous point of execution with each iteration. You're just unfolding or unrolling all these iterations of the loop. Okay? So again, use this with care. It is handy every now and then. If in doubt, use function composition. It's much clearer. Here's an n-bit ripple carry adder with a loop. Because this adder has a chain, it actually maps pretty naturally to a loop. Right? So what do we want? Well, we want to instantiate n full adders. Right? So we have the same signature here. So it's RCA, but with a parameter n, that's an integer. And so we have the S values over here, S0 through Sn-1, so that's a bit n, and then all the carries, right? The first carry is carry in, this is C0, and then we have up to Cn, so this is bit of n plus 1. And then we get to this loop. And what this loop is saying is, well, let X full adder A of 0, B of 0, C of 0, and then S of 0 is X of 0, C of 1 is X of 1. That's iteration 1. Okay. If you have more iterations, then it will go and run and unfold this into let x equals full adder a1, b1, c1, s1, x0, c2, x1. And it will just repeat the code, right, n times. That's all it's doing. It's not doing a sequence of iterations. It's just repeating the code. Okay, any questions? So, as I said, use for loops sparingly. In recitation, you'll see there are several problems that ask you to implement things with for loops and without for loops, and what you'll see very quickly is that for loops generally make for slower circuits because you'll create serial chains of gates when in fact you can do trees of gates, which are faster. One final feature, you also have if-else, like here, right? So this function computes the maximum of two 4-bit values. It initializes result to B, and then if A is larger than B, it sets result to A and returns the result. You can also do this with if-else, right? So if A is greater than B, the result is A, otherwise result is B. Just like for loops are nothing like for loops in hardware. If statements and if-else statements are implemented very differently. This is just a fancy way to have conditional expressions. So they're translated to multiplexers. They're just expressing multiplexers. What this circuit is going to be synthesized to is the compiler is going to say, okay, so you have an if-else where you're assigning to the result in both branches. So if A, so I will synthesize a max for result, and then I'll assign it A if A is greater than B, right? So this is the condition, the selection input into the max. And otherwise, I will just assign B to it. So that again is a max, and again, remember that just like with conditional expressions, all branches are evaluated. You're not executing this or that. You're generating a max. You're writing code that generates a multiplexer. And we also have case statements, which are analogous to the case expressions that we saw before. I'm not going to spend time on this. Just see the tutorial if you want to use them. That describes their syntax in more detail. So the takeaway here is that you can now build circuits with constructs similar to the ones you use in software programming languages. However, their implementation is quite different. So remember, parametric functions are typed and types are instantiated, and this is in fact the only thing that's actually quite similar to what happens in a software compiler for a programming language that has generics. Everything else is quite different. Functions are inline. There's no calling convention. You're not calling some other part of the code. You're just plopping the entire implementation of the circuit inside your circuit. Conditionals are translated to multiplexers, and you evaluate all branches. For loops are unrolled, and then what remains is just an acyclic graph of gates, which is something that you can implement with combinational logic. Right? So you can take all these constructs that are similar to software, to what we've seen in software, and in fact generate a combinational circuit. But it's very important that you never forget that you're designing hardware. Because in hardware, you can, for example, do many things in parallel. And if, for example, you write a for loop, you're going to do things more serially than you need to, often. Okay, any questions? So far we've been focusing on getting functional specifications of the circuits. Let's talk a little bit about performance. Right? It is very important to consider the range of choices that you have when designing a single function. And often it is the case that you'll have widely different implementations that have very, very different delay, area, and power characteristics. This is no different than software design. Right? You're given a problem, you write a high-level circuit description, give it to the synthesis tool. The synthesis tool doesn't do magic. The synthesis tool is not going to translate, some bad algorithm into the optimal algorithm. Right? The synthesis tool will do some optimizations, but if you give it a bad algorithm to begin with, it's not going to do well. And this is just no different than programming software. You've seen this, right? You've coded bubble sort and quicksort. the compiler is not going to transform bubble sort into quicksort. It just won't do that, right? You have to give it the algorithm. So to see what interesting trade-offs we have between area, delay, and so on, let's look at a couple of different other implementations, right? And this is important because computers have a lot of others, and the other that we've seen so far, the ripple carry other, is simple but it's very slow. So for your processor, you'll want to have a faster one. And this is the last exercise in lab 4. So remember, we already saw this, right? You have an n-bit ripple carry other, and the problem here is that there's this chain of carry propagations, right? And remember, we're interested in the worst case delay, which happens when we're adding, something that's a lot of ones to something that's, 0, 0, 0, 0, 1. So that 1 is going to turn this carry from a 0 to a 1, and this carry from a 0 to a 1, and so on and so forth, until we flip the last bit of the output. Right? So what is the propagation delay of this? It's n times the propagation delay of the individual full adder, right? And just to make it a little bit more formal, because we don't care about the particular values of this, we're just going to look at algorithmic trade-offs, we say that this is theta of n, or order of n, or order n. And this is just saying that the latency of this adder grows linearly with the number of input bits, right? So a bit of a review in case you don't know about asymptotic analysis. This theta of n notation essentially means the following. If you have a function g of n, we say that g of n is theta of f of n if there are two constants, c2 and c1, that lets you bound g of n except for small values of n when multiplied with this function f of n. What this means, generally f of n is a simpler function of g of n. In practice, what you'll be doing is dropping every term except the term that grows more rapidly, and then dropping all constant factors to derive this f of n. But just to give you an example, we say that if I give you n plus 10, right, we say that this is order of n because you can find, n here, and let's say 2n, and after this point over here, this is an upper bound, this is a lower bound. Right? This is always smaller, this is always larger. So that is what this notation is letting us do. But the whole point is that this is letting you drop the factors that don't matter as n grows. So this is a slightly more complex example, n squared plus 2n plus 3. We say that this is of order n squared, quadratic with n. Right? Okay, any questions? So, the first adder that we're going to see that improves performance quite a bit, but at a cost, is what we call a carry select adder. So suppose that instead of having a 32-bit adder, we just do the following. We get the upper half of the adder, and we just compute two possible values. We say, well, the carry, the 15th carry, like C15, can be 0 or can be 1. And the problem is we have this long chain and we don't know what C15 is for a while, and then it has to propagate through the whole upper half. Let me just compute both values of C, right? So have a 16-bit adder that takes a carry in of 0, and have a 16-bit adder that takes in a carry in of 1. And then, when we know the right value, we'll just select the right one. Right? So then, essentially the carry out of the low half is selecting the correct version from the two that we computed. Why is this good? What have we achieved with this? What's the propagation delay? Is it better or worse than before? Yes?
It's better because now we've made sequence with two parallel.
Exactly. So now the delay of this 32-bit adder is the delay of this lower half plus the delay of the max. Right? And that's because the upper halves finish in the same time as the lower half. Great. So you could say, okay, we'll do ripple carry adders here, right? And then we'll just we'll just cut the delay in half. But you could keep going, right? Note that this doesn't say a 16-bit ripple carry adder, it just says a 16-bit adder. So how you implement those adders is up to you. And in fact, you could apply the same strategy recursively, right? And build this 16-bit adder, and this 16-bit adder, and this 16-bit adder using a carry select adder. 8 plus 8. Then its 8-bit adder would be a 4-bit adder and a 4-bit adder. And if you keep going, what you'll get is that the propagation delay is logarithmic on it, right? Why? Because at each level, we're cutting the number of bits in half and adding one layer of logic. Therefore, as we double the number of bits, we're adding a constant factor that's always logarithmic. Any questions? Okay, so you can get log n delay, right? We can go from linear to log n with carry select adders. That's awesome, right? Except there are some problems. Can anybody guess what problems we might have here? Is there something that's not so good about this? Yes? Yeah, we have 3 copies of each adder, and each of them has 3 copies of smaller adders. There's a lot more area here, and we have the max, and that also takes a while. That's a much more area. Now it's faster, but it comes at a price. There's another detail that will become very obvious in Lab 4, because you have an exercise in Lab 4 that has to do with this, and it has to do with this carry out signal. It's driving a lot of inputs, and that makes it slow. That's, we say, a very high fan out input, and that makes this add significant delay. And you'll see this in much more detail in Lab 4. So let me introduce, in the last few minutes of the lecture, the most sophisticated type of adder, which is one that I recommend you build. And we'll finish the discussion of this in recitation. But let's see the key insight of carry look ahead adders, which is actually a very general insight. What we want is to have some circuitry that computes all the carry bits in logarithmic time. Now we've seen a way to compute the whole addition in logarithmic time, so hopefully that's possible, right? And so instead of having this chain of carry-ins, of carries propagating from input to output, we're going to derive this carry generation logic that just from the A's and B's and then the C in value is in logarithmic time going to derive all the carry signals there. Now, the key idea, of course, is to transform this chain of carry computations that we have in the ripple carry adder into a tree. And this, if I give you a chain of AND operations or a chain of XOR operations, you can just reassociate terms, and it's a very common transformation, right? We do it all over the place. Tools do this automatically. But if you have carries, that's not so obvious now, right? Because it actually is a chain, and there's no way to reassociate terms that makes any sense. So we need to do a little bit of algebraic manipulation to get things into a form where they actually can be made into a tree. And here's the transformation. It's actually a very intuitive way of thinking about an adder. So remember, a full adder has these equations, right? It's A, XOR B, XOR Z in. That gets you the sum. We're not going to care about this equation, but we do care about the C out, how you compute C out from A, B, and C in. And remember, this is the majority function over here, which we can just write as shown here, right? A, B, or A or B, and C in. And then we can rename terms. We can just say, we're going to call A and B G for generate, and A or B we're just going to call P, which stands for propagate. And those names are kind of weird when you look at them, but they're very intuitive. Why? Well, because if G is 1, what happens? Well, if G is 1, then the carry out is 1 regardless of what the carry in is. So we say that the full adder generates a carry. The carry is going to be 1 no matter what the carry in is. And then if P is 1, so if propagate is 1 and generate is 0, then the carry out is the carry in. Right? When we say that the full adder is propagating the carry. And note that these values don't depend on the carry in. And the key insight here is that you can compose these signals hierarchically. And the moment that you understand this, the moment that you understand just this slide, you can go and implement all sorts of carry look-ahead adders. Let's do this. So, if I give you a 2-bit ripple carry adder, can you give me an expression of C2 as a function of C0 and then the generates and propagates of individual signals? Well, you can just expand it. C2 is G1 or P1 and C1, and then you can expand C1 here. So P1 and G0 or P0 and C0, and then reassociate terms. And if you reassociate terms this way, now the light bulb should start going off, because this is a generate term for both 1 and 0, and this is the propagate term for both 1 and 0. And what does that mean? That means that I can join together these individual generate and propagate signals into generate and propagate signals for groups of full adders. And why is that good? Let's do a 4-bit adder. Well, you can build it up, right? What is G10? This is just what I type here, right? G1 and P1, or P1 and G0, and P10 is P1 and P0. Right? The lower half of these 4 adders propagates if both adders propagate, and generates if this adder over here generates, or this adder propagates and this one generates. What about the upper half? Same thing. Can we combine them? Sure. So now you have a single generate and propagate signal that goes from C0 to C4. And you can just say C4 is G30 to, or P30 and C0. And now the key step here is, do I need to do these two serially? Do they depend on each other? No, they're parallel. So I can do a tree. I can implement this as a tree. And once you understand this basic fact, and we'll see this in recitation tomorrow a little bit more, you can build the whole family of carry look-ahead adders. But this is the key insight, that by reassociating things in terms of propagate and generate signals, you can build trees of generate and propagate signals that let you derive these very far away carries in a logarithmic number of steps. All right, that's it for today. Thank you.